Okay, thanks for the introduction. We're going to get right into this because we got a lot of ground to cover in the short period of time we have. So on the agenda, I'm going to go through the different parts of the J1939 communication stack, the physical part of the physical layer, which is dictated in the specification SAE J1939-11. We're going to go through the data link layer, it's in -21. Data fields, Dbc files, what they do for us. We're going to define some acronyms, PGNs and SPNs. There'll be a bunch of acronyms on top of that defined, and diagnostic messages, DMs, will be covered. And they're documented in J1939-73. There will be 3 examples that I will use to get these concepts across to everybody. And the different parts of the J1939 communication stack, as it's called. This was covered in CAN Basics, which is a prerequisite for this particular training, and I hope that you all have that. It makes a lot more sense. This a similar slide to this was used in CAN Basics. Shows a typical CAN network here, which is 4 devices on it. There can be quite a few more than that. It shows that it is the physical layer that sends the 1s and 0s reliably across this network and handles all of that. That covers the voltages, the impedances, things that dictate physical layer transmission on this network, or the specification that dictates the transmission physical layer we're going to be working with today is the J1939-11 specification. The -13 talks about the actual connector, and these other ones go with different types of wire and different speeds, and CAN FD when you get up here. So we're just going to deal with a subset of what's here on the physical layer. The data link layer puts a frame around those 1s and 0s so you can understand what they are. It's the purpose of the data link layer. It's specified in J1939-21, and for classic CAN, and -22 for CAN FD. We're going to work quite a bit, understand quite a bit about 21. Those 2 subjects there were covered in CAN Basics. We're going to get also to transport protocol, which is specified in -21 and 22 as well, which wasn't covered in CAN Basics. That's specific to J1939, as a lot of this stuff is, and it's for sending larger blocks of data, larger than a classic CAN frame can hold, larger than 8 bytes, which is what a classic CAN frame can hold. So transport protocol, and then we're going to get to the application. The application layer is where 95% or so of the work is done in J1939, and the specifications we will work with are -71, -73, and I'll mention -84. So these are, again, J1939 specifications. I threw this slide in. There's 10 of these specifications, which isn't all of them mentioned on this slide, and the 5 that are highlighted are the ones that we'll be working directly with in this presentation. Okay, and these are a lot of information in these slides. I wanted to make the point that they're not outrageously expensive. For $600, you can have all of these highlighted. These are purchased from SAE.org, the nonprofit standards organization in the US that governs, creates, and maintains J1939 as a standard, as one of their many, many standards. So again, the ones we're working with in yellow, best to buy them, best to know them. They're really needed if you're going to work in this industry and understand this stuff and work with it on a daily basis. This is an example of just a cheat sheet I put together. The only point I want to make here is you put a little Excel spreadsheet together, you hot link into your actual documents, and then you don't have to fumble around trying to remember what document covers what subject. If you want to understand PGNs, you got a primary and a secondary document, and you can click here and open those documents quickly so you can understand more or find a particular PGN. Same with an SPN, you want to find a diagnostic message, you have your primary and your secondary documents that are related to that subject or that information needed. Just a quick cheat sheet to help you navigate and move more quickly within this industry and within these standards. So the physical network, 250K twisted shielded pair, defined in -11. That's what we're going to talk about here. I have covered this material in CAN Basics for review. These are 3 slides that were in CAN Basics all crammed into one here. It shows you what a typical network looks like. Every network has two terminators, a trunk cable, and drop cables of some length. And then we talk about the voltages on the two different CAN lines, CAN low and CAN high, and how they are read, and the time segments and how they're sliced up, and then how bitwise arbitration works, which is an important concept to understand for this. The two things to take away from CAN Basics to understand what I'm going to teach here is when one device sends data on any CAN network, all of them receive it. And bitwise arbitration says that when two devices start sending at the exact same time, the one device with the lower ID identifier is the one that wins arbitration because of bitwise arbitration. That's the way bitwise arbitration works. Review CAN Basics, a prerequisite for this course if you don't have that down. We're going to look at CAN frames and a data link layer here. So this is pertinent to J1939. A lot of different standards that run on CAN use a similar breakdown of the data link layer. Some of them use the data link layer completely differently, but CAN defines the fact that we have an arbitration phase, and J1939 defines how that arbitration phase is going to be used. Here's a bunch of CAN data. A couple of points here. A lot of CAN data on a bus. You probably won't ever understand all of it. Different protocols on a bus sometimes. You can grab your J1939 frames and various different filtering methods, and I want to make sure you can understand those. The goal here is to be able to understand how to take a J1939 CAN frame, classic CAN frame, apart and know what it means. Right? And these are J1939 identifiers. These are J1939 frames. A lot of hex data doesn't mean a whole lot in this form. We're going to get into it here and figure it out. Here's example one. Right off the bat, we're going to jump into example one. So example one is a message here that includes 7 bytes of data. So the first 4 bytes of this are the identifier, and then there's 3 bytes actually in the data phase. So 7 bytes total, 4 identifier, 3 of the data. This particular cut was taken from a J1939-84 log file as an example. This is, I happen to know this is a request message, and this tool was requesting a DM21, and it received that DM21 down here. We're going to look at the request portion of this message, mainly so we can understand the identification phase here, and we'll also understand the data in that request message, so we can see what tools to use to break down this and understand every single little bit of what it's telling us. So a lot of information on this slide. So up here, well, first of all, right here, I repeat that exact same hex data that we had in the previous slide. So here's the hex data we want to understand. I have put a block here that shows generally what a J1939 CAN frame breaks down as. Breaks down as a starter frame, a priority, 3 bits, the PGN parameter group number, 18 bits there, the source address, 8 bits there, the data length code, 4 bits there, the data itself, which can be from 0 to 8 bytes, and then the cyclic redundancy check. Okay, then below that, I show you what's typically shown to the application. So the CAN controller pulls the starter frame off, it pulls the data length code off, and it pulls the CRC off, checks to make sure the CRC is right, the data didn't get corrupted or isn't in error, and passes accurate data up to applications. So here we have the data we're going to analyze, and the ID phase we're going to analyze. First thing to understand is it doesn't, the ID doesn't break down on even byte boundaries. So the 1.8 is the hard part to understand. Everything else pretty much breaks down on byte boundaries in here. The data certainly, there's anywhere from 0 to 8 data bytes. Right? The parameter group number here is 2 bytes. The source address is 1 byte. But here we have this funny looking byte, this priority. Well, first thing to understand is an extended CAN header is 29 bits, and I showed the bits down here. Right? 29 doesn't divide evenly by 8 bits per byte. So this most significant byte is only 5 bits. So the first character can only be a 1 or a 0, depending on this bit right here. And after that, we have 4 bits of the next nibble here. So a 1-8 is what was transmitted. The message has a priority of 6. How do we get that? Well, you can see the 3 bits in here that are priority, and there's a couple of the control bits transmitted here that I'll get into in a little bit. All right, so there's our whole message. The 1-8 is a priority of 6, as shown here. These 2 bits I'll talk about in a little bit. The EA00 translates into a decimal 59904. If you look at J1939-21, you'll see that that's a request message. And it could break down further than that. What is it requesting? Right? EA00 is a request message. Out here we have source address, which is the next byte, and the source address in this case is F9. If we look in J1939 DA, digital annex, then we will see that an F9 is the service tool. It translates to 249 decimal, and 249 decimal is the service tool. So we know a service tool is requesting something using the request message. What is it requesting? We get into the data to figure that out. 00C100, it is requesting PGN 49408 is what it's requesting. If we look in J1939-73, we see that that PGN is a DM21. So we figured out from breaking this down into bits and bytes that the service tool, F9, is requesting, and it's actually requesting from 00, which is the engine ECU, a DM21 right here. That's what it's requesting. And it's using a priority 6 message to request that. So a lot of information there. We broke that down pretty much completely, but we're going to go a little bit further here. So a PGN, a parameter group number, or a PG. The PGN itself is an identifying number for a group of parameters. Right? The PG refers to the number only. The PG refers to the group of parameters. So it's a subtle difference, but it's an important difference. The PGN follows a very specific format defined in our -21 specification. And if you look at page 8 of -21, you'll see that it breaks down the full definition of how the 29-bit identifier, extended CAN identifier, is used in J1939. On page 14, it talks about the PF and the PS fields. So this is Pdu format and Pdu specific fields. These are double acronyms. Pdu is protocol data unit. Right? So we have within the PGN, the parameter group number, which is 2 bytes. It breaks in half PF and PS field. Okay, PF field is EA in this case, in this example. PS field is 00. Okay, we can take them to decimal, and you get 234 for the PF field. Okay, so the whole point of this is every parameter group number in J1939 conforms to one of 2 formats, a Pdu1 format or a Pdu2 format. Okay, I talk about how this all works in the next slide, and I actually repeat this block here, which is table 4 out of -21 in the next slide. This is kind of critical, but we know what protocol data unit, double acronym. We know a PF protocol data unit format and a protocol data unit specific fields, and we're going to go further into that. So Pdu1 format, if the first byte of the PGN is somewhere from 0 to 239 or 00 to EF hex, the second byte is the destination address. This is the case in example 1. Right? This is definitely the case in example 1. If we were dealing with a Pdu2 format message, that would mean the first byte would be somewhere between 240 and 255. Then the second byte would be a group extension. And so that's important to understand. what this gives us is an ability to send addressable parameter group numbers, have addressable PGNs, and it gives us 240 addressable PGNs, and it gives us 4,096 non-addressable PGNs. And the way that's calculated, so we get 4,336 total PGNs. There's 2 pages of PGNs. I'll get into that in a bit. That's one of those control bits I kind of skipped over. So we have a total of 8,672 parameter group numbers to use in J1939. 8,672 possible PGNs. Example 1 in this case is EA00. EA is 234, falls in this range. It's a Pdu1 format message. Second byte is destination address. Second byte is 00, the engine ECU. So the engine ECU is the destination address. Okay, we have a Pdu1 format message addressed to the destination address engine ECU in this case. Moving on from here. Okay, so we're going to repeat that bitwise breakdown of the message that I showed you. And the reason I'm going to repeat it is I want to talk about these 2 control bits that we kind of skipped over. So the control bits, in this case, control bits in the CAN ID, these are the data page and the extended data page. Okay, and this table, table 3 out of J1939-21 shows you the data page and the extended data page. So the first bit here, data page, if it's a 0, we've got a J1939 PGN, page 0 or page 1 PGNs. That's how we double the number of PGNs at our disposal here. If it's a 1, then it's either reserved for future J1939 use or it's defined in ISO specification. That means the definition of the identification phase is different. So J1939 definition doesn't apply. So we're only really dealing with J1939 PGNs here. When the extended data page is 0, that's really all I need to say about that. So you understand how all of the rest of this format breaks down and works at this point. Okay, so we're going to jump into the data field now. This is the applications layer stuff. We got to talk about the DBC file in order to understand that. So CAN frames can include anywhere from 0 to 8 data bytes. Classic CAN frames. The large majority of J1939 frames are 8 data bytes. You'll see some control frames that are 3 data bytes. We've already seen one of those. We analyzed the request message, which is a 3 data byte message. Okay, so here we have another fairly random J1939 data stream. I've highlighted one particular frame. We know how to take the PGN apart, the F004. We know how to get the source address and the destination address, which is global here. We know how to get the priority, which is 3 here. It's got a length or a data length code of 8. And there's the data, and there's a timestamp. It's the data we're going to worry about now. Let's look at the data. How is the data defined? Okay. To understand the data, you got to understand how DBC files are used. You don't really have to understand every little quirk about them, but at least how they're used and what they do. So you got a CAN bus out here. You've got a CAN device attached to it, whether it's a complete embedded device or an interface feeding an application on a program, doesn't really matter. The raw CAN data comes out of the CAN controller on USB or in any other form. And the raw CAN data needs to be translated. The DBC file identifies the messages, identifies the data, scales and offsets the data, identifies the location of the data, and labels the data. So the DBC file tells you 2 major things. One tells you how to break down the CAN ID, what message is being sent, how to basically what PGN is being sent, and how to read that data, how to scale that data, and how to offset it. So you get an output from an application that uses some or all of the data within the DBC file and uses the raw CAN data. The output is meaningful data. Here we have meaningful data coming out of this device, regardless of whether it's an embedded single function device or a complicated test program running on a PC. This is the concept. So we know what the DBC file does. Scales, labels, isolates, and offsets the data so it's understandable and readable. How could that be? Well, let's give you an example of that. An example's coming up here. So first we're going to understand the SPN, and the SPN is explained in J1939-71. SPN stands for Suspect Parameter Number. It's again an identifying number of a single parameter. SP is the suspect parameter, that is the single parameter within a parameter group. SP can't be broken down any further than it is. It is either from 1 bit or larger. And SP can be many bytes, or it can be 1 bit long. There are many SPs that are 1 bit long. It's broken out again as far as you can go with it in an SP. It is value as transmitted in a CAN frame. It is a signal. That's what we're calling it here. An SP is a signal. So I've got some examples of 4 SPs that all are within 1 PGN, and they're consecutive. Engine turbocharge 1 compressor intake pressure is a 2-byte signal. 1/128th kPa per bit. It's a pressure measurement. It's offset by 250 kPa, and that's the range. All right, the same with 2, 3, and 4. So that's just an example. There are over 20,000 SPNs in J1939. So there's a lot of signals defined in J1939. They're all spelled out in the digital annex, J1939DA. You need that to possibly understand what all of the signals are that J1939 transmits. Here is another example of block of data shown a little bit differently from a different tool. We know the PGN, we know the source address destination address, we know the data length code. They're all 8 bytes per frame here. The channel is just what channel it was received on, so we know what all of this means. Let's get into the data itself. Timestamp rounded off here, and this data was received, but these are the magic bytes, the data. What does the data tell us? We're going to pick one signal out of this data, and we're going to analyze that signal all the way down to the bit level. Here is, again, I repeated the data, D1 through D8, 8 bytes of data. All right, so PGN F004 translates to 61444. We can look that PGN up in the digital annex, and the name of it is Electronic Engine Control 1. It's abbreviated EEC1, okay? We're going to look at engine speed, which is one suspect parameter number within that PGN, within that parameter group. Okay, so this is the parameter group, 61444. This is the suspect parameter within that group that we're going to consider. Where's all that defined? Well, this is a cut out of a DBC file right here. And we filtered on 61444, and we picked out one signal, which happens to be called engine speed. It's a 2-byte signal. We've got a resolution for it. We've got an offset for it. We have a suspect parameter number that identifies it. And we know the parameter group number itself is got a data length code of 8, and we know the abbreviation for it. So now let's get into and figure out this data itself. I'm going to show you a cut out of, and I know it's an eye chart, just a quick cut out of the database editor 3. It's a free database editor downloadable from Kvaser.com download section. I've filtered through the many PGNs within it, and I've highlighted EEC1, which is the PGN we're talking about, and it's shown here. When you highlight EEC1, it shows you that PGN out here in a graphical breakdown, and it shows you all of the signals, or all of the SPNs within that PG. Underneath, I've highlighted engine speed, the data, the location of it, the offset of it, the range of it, a few other parameters related to it are all highlighted down here. Just want to show you that where this information comes from, and one way to read it out of the DBC file is with Kvaser's downloadable database editor 3. I'll repeat the data up here, so isolating the SPN and figuring that out. So the J1939 DA tells us that SPN 190 is in bytes D4 and D5. Okay, data in D4 and D5 is 5014, as we can see from the data stream we pulled this out of. J1939 DA also tells us that it's Intel byte order. We know this is little n first, as opposed to Motorola byte order, which is big N first. So little n first, we have a 5014. This is the least significant byte, little n. This is the most significant byte. We write that hex number as 1450. We translate it or convert it to decimal. We have 5200 is the decimal value that's transmitted here, right? So the J1939 DA also tells us that the resolution is 0.125 RPMs per bit. So we multiply that number of bits by that number of RPMs per bit, and we get 650 RPMs. The truck I was sitting on when I took this data was idling at 650 RPMs. And that's the signal that is used by your average tachometer, or any tachometer reads that signal and displays that number of RPMs as the truck's RPMs. That's an example of J1939 and an example of taking apart the data. So that's example number 2. CAN frames and transport protocol. There's no real, it's kind of an example associated with this, I guess. So this is a string of data that I pulled off of a vehicle with a tool, a rather specific tool for reading-84 compliance. You can see what was transmitted and what was received by my tool. Transmitted, my tool transmitted the request message, which we're familiar with. There's a little bit of differences here, but this is basically the request message that we saw in example 1. Right? And I put this out here, what message this is, the name of the message that it's transmitting, or that we're decoding here. We can see it's a little bit different of a request message. It goes to the global address, not to the engine ECU. This being source address of this request message is the service tool, the F9, whereas before it was the other way around, I think. And it's requesting a different PGN. It's requesting PGN FEEC, which FEEC is PGN 65260. The digital annex would tell us that's the vehicle identification number. Here's a PGN that takes, I think, 17 bytes of data in this PGN. We can't put all of those bytes of data in one CAN frame. So the answer to this request coming from the engine ECU is sent in a transport protocol format. Our tool receives 4 messages that contain the data that answers this request. The first of those 4 messages is the transport protocol command message, and it's here. And I won't break down everything in it, but it basically, 2 things are, it says there's 3 frames of data coming, and this is PGN FEEC. So we embed the PGN that's actually going to be transmitted within the data here in this transport protocol. Okay. The next 3 messages are the data themselves. There's a sequence number. The first byte takes a sequence number. Right. The first byte of the data. This is all header here. This is all identification phase. First byte of the data is the sequence number, and then we get ASCII characters, which represent the vehicle identification number. The sequence ends with the star. 2-way ASCII is a star, and the rest is filler. And these are all transport protocol data frames, data transfers. 60160 is a data transfer. 60416 is a connection management. If you took these PGNs here and translated them, you'd see that that's what they are. So hopefully that explains transport protocol in an example to you. Didn't really number that example. There are two types of transport protocol. One is a BAM. It's called a BAM, which stands for Broadcast Announce Message. The originating node just simply sends the data in transport protocol format, and everybody on the bus receives it. That's the way a BAM works. There's also a request to send, clear to send method of transmitting a transport protocol message, and that's where the originating node sends a request to send. The receiving node responds with a clear to send and tells the originating node how many bytes of data can be sent over in each group, and then the originating node can start sending those bytes of data in that size groups, waiting for other clear to sends until the sequence is over. That's a request to send, clear to send, sequences to send the transport protocol data. I'm going to talk a little bit about CARB, California Air Resource Board, and California Code of Regulations. So the original reason, I mean, I don't know if the reason, but one of the pushing factors for J1939 was diagnostic messages, universal diagnostic messages that were standardized across manufacturers that could be read by a tool, so we could read faults and maintain trucks and maintain vehicles. Right? That was some of the original use. Used to report the history and the current state of a vehicle. They're legislated by California Air Resource Board, so there are laws in the state of California that say vehicles in the state must conform to this communication standard. They were primarily used and still are used to a large extent for emissions-related fault detection, standardized across all U.S. manufacturers. And standard scan tools can read these messages, and standard plug can plug into these vehicles here. This is a Kvaser tool, J1939 connected leaf light tool. And so the messages themselves are defined in J1939-73 as diagnostic messages, and a method to test and evaluate the scan tool is provided in J1939-84. Which is a scan tool test. We can quickly move on. Diagnostic messages. I'm going to give you a third example here in a bit. So there's broadcast messages, there's on-request messages, there's diagnostic messages. Some diagnostic messages are on request, some are broadcast. Understanding the diagnostic message, that's pretty much all part of J1939-73. Here's 5 examples of diagnostic messages. I'm going to get into DM1 and explain the DTC, the diagnostic trouble code, which is a concept used across quite a few other different diagnostic messages. Not all of them, but a bunch of them. There's, I think, 59 different diagnostic messages. There's no way we can study them all, so let's look at DM1. First thing we're going to understand is, what is a diagnostic? A diagnostic is code that runs to perform a specific test within the vehicle. So an ECU tests for hundreds of different failure conditions. Each test requires the engine to be in a pretty specific condition to run and test for some parameter. When those conditions are met, a diagnostic will run and will perform the test. What is a failure mode indicator? A failure mode indicator is just what it sounds like. There's 31 of them, and it's a value reported within a DTC, a diagnostic trouble code, to indicate what the failure mode is. And 2 examples I put up there is FMI 1 is data valid but below normal operating range, most severe level. Failure mode indicator 2 is data erratic, intermittent, or incorrect. And there's quite a few others. They're defined in J1939-71. There's 39 of them, 31 of them total. Okay, there's a couple other random bits in here. One is the conversion method. It's a single bit that's referencing an old structure for a DTC, which isn't really used anymore. So the conversion method bit, don't worry about. There's the occurrence count, which is simply a count of how many times that particular code has been set since a clear was received. So, and we'll see a little bit of an example of that. The diagnostic message, again, -73, again, by regulation of California Code of Regulations 1971.1, pretty much defines what data has to be transferred in diagnostic messages. The standard scan tools read them. California Air Resource Board legislates compliance with it. The -84 tool specifies scan tool functionalities and a test for compliance to that standard. And there's a new standard out called J1939 and it's basically a dynamic -84 test, I call it. It tests for in-use monitor performance ratio compliance. They're reported in DM20. That's way more than I can do in an hour right there. So we're just gonna leave it at that kind of a mention here. Example number 3, DM1, diagnostic message 1, active diagnostic trouble codes. Here is what it would look like as reported. Raw CAN data on the CAN bus. We know this is a DM1 because we know how to read the PGN, FECA, and we know that's a DM1 because we can go to the DA, the J1939 DA, digital annex, and we can find that, and it labels it a DM1. Also, the specification -73 will explain everything about a DM1. We know it's a priority 6. We've already done that, and we know it's source address 00, so we know the engine ECU is sending it. That's also in all the DA. It's in the DA. Okay, this is all part of the arbitration phase and defined in the data link layer in the digital annex and defined in -21 as well. So DM1 is, as a diagnostic message, is defined in -73. And how to use the data is totally defined in -73. We're going to get into the data here. This is going to show you how to use the data. So first I've highlighted 4 bytes of the data. I've skipped 2 of them. I'll get back to them in a little bit. Okay, these 4 bytes I've highlighted because they represent a diagnostic trouble code. A diagnostic trouble code is an SPN, suspect parameter number. We know those. Okay, an FMI, a failure mode indicator. Talked about that. That's here, these 5 bits. Okay, SPN conversion method is 0. I told you that's old history. We're not going to worry about that. And then there's an occurrence count. These bits make up the occurrence count, and that's a 1. Okay, so SPN is hex 66 or decimal 102. Again, we look up in the DA, we look up all the SPNs. There's over 20,000 SPNs defined in J1939. I sure can't teach you those here. Over 20,000 of them. We can look up SPN 102, and it's called engine intake manifold number 1 pressure. We can look up a failure mode indicator of 2, and it's data erratic, intermittent, or incorrect. And we got an occurrence count of 1. So this tells you one time. This tells you this diagnostic trouble code is set. This code is set, and once since clearing, the engine intake manifold number 1 pressure has exhibited erratic data, intermittent or incorrect data. That's what this DTC tells us right here, these 4 bytes. Okay, that information is in -73 as shown down here. These are cuts out of -73. All right, so moving on to the next slide. So we know what this diagnostic trouble code tells us and how to read it. We'll go back and let's look at the 43FF, the first 2 data bytes of the frame, of the DM1 frame. And we're going to look at 4 different things here. Lamp status, which is what these 2 bytes are. And lamp status is all explained down here and what these bits mean. Right? Red stop lamp, protect lamp, different lamps can flash or can be on steady or off. And that's all communicated via this table and these sections in these 2 bytes. All right, so that's lamp status, and then we've got SPN, FMI, and CM and occurrence count. We know what those are. Okay, then we got this little highlighted message down here that the following form applies. A, B, C, D, B, C, D, B, C, D. What does this tells us? It tells us A is transmitted once, and B, C, D is transmitted for every diagnostic trouble code set on this vehicle. Okay, right now we have one diagnostic trouble code set on this vehicle. So we've only used 6 of the 8 bytes available to us within this CAN frame. We use filler for the next 2 bytes. If we had 2 diagnostic trouble codes set on this vehicle, then we would use 4 more bytes, and we would have to go to transport protocol to do that. I've seen DM1s with 25 different codes set on them, and they're big transport protocol messages at that point. So that explains a lot. That shows you when and how transport protocol is used, how to read a DM1, how to use this sequence to read a diagnostic trouble code, which appears in many other diagnostic messages as well. There's a lot in there. So DM1 is a variable length diagnostic message. Okay. What helped me understand all this I wanted to cover is own the standards, know the standards, use the standards, and research the standards. It's not real easy stuff. You cannot do it without having the standards. Okay, be able to follow a signal all the way back to the data link layer, like I've shown you how to do here. Confirm that the tools that you're working with are reporting the correct data if there's any doubt. I've found a lot of mistakes in tools. You can spin your wheels for hours that way. Okay, and own the DA, know how to use the filters within spreadsheets so you can filter and find the signals and the parameter groups you're looking for within the digital annex, and you can understand that data, right? Where to go for more? By the standards at sae.org. Consider protocol stacks, training, and partners. You can just hit the search and type in J1939, and you'll get a bunch of data on Kvaser.com. And you'll get more training resources as well if you do that. There's about at least 4 other papers I've published, 4 papers that'll help you understand J1939 up there that are all fairly much on the hopefully beginner side. There's my email. Use it. Send me questions if you like. I'm going to wrap it up here. Thank you very much.
Thank you, Brian, for providing us with that overview of J1939. We're now briefly going to spend a few minutes talking about CANLab and its application to J1939 for the developers and diagnosticians. So what we're going to do quickly is we're going to discuss CANLab, its overview, its workspace, its J1939 support, and then its CANLab, the scripting available for CANLab. So CANLab is a multi-function bus analysis tool allowing for the recording of signals, sending and replaying messages, while also incorporating a scripting environment. CANLab supports several ATI and Kvaser CAN, LIN, and CANFD interfaces. When you first start CANLab, you are presented with a blank workspace. This is where you can create a central location for your databases, scripts, recorders, and data viewers. The user has access to familiar Windows menu and toolbars, allowing for quick immersion into the CANLab workspace environment. On the left-hand side of the workspace, you will find the main navigation panel. And the first item you see is your channel manager, where you will select your bus interface and its properties, such as baud rate and channel selection. This is the only step that has to be done offline. All other actions can be done while online and acquiring data. Below the channel manager is our data source manager. This is used to add your data sources to CANLab. Multiple monitors, recordings, and channels can be added at any time that the workspace is active. Below that is the database manager. The database manager is where all active databases are added and organized for use in the workspace. Below there is the message logger. Message logging is the process for saving raw messages for later decoding and post-collection processing. Once we have our hardware configured and our databases and recordings added, we then proceed to look inside of the workspace and add objects to view data. And of the multiple screen objects that are used in CANLab, the CAN trace is the most common for observing bus traffic. If a DBC file is available, the signals within each message can be seen. We can also use this to set up highlighted messages for easy identification, as well as add protocol decoding. So here we see a demonstration of message highlighting. So we right mouse click on the message. We start by adding a message, and then we define its highlighting style. We can give it a name so that it can be used later. We can change its background color, its font, and its foreground color. Once we have that defined, we can add a data item that we want to observe with this figure. So in this case, we're going to be adding a signal based on a sawtooth, and we want to set it that when it's greater than 300, we want to change from standard messaging to a highlighted message. You can see here, when it goes above 300, it changes red, and when it decreases, it goes back to white. Here you can see the same example set in a scrolling message format. We can have multiple highlighters in either standard or extended bit identifiers. The process is the same. We type in a message. We double click it. We can add a highlight style. We can either choose the red, or in this case, we're going to give it a differentiating highlight by changing the color, the font, font style and size, and the front, and again, the foreground color. Now this one's going to highlight every time that it sees the message, regardless of its state. CANLab also supports 3 protocols: CCP, XCP, and keyword protocol. We can decode those by right mouse clicking inside the workspace, select the command interpreter, select the protocol we wish to interpret, then set the CRO and DTO to the appropriate values, and CANLab will begin to stream the data in a interpreted format. The CAN replay object allows for one or more pre-recorded log files to be played back, either into CANLab or into a testbed situation. There are radio buttons that control the playback, such as play, stop, pause, etc., and the options to change the playback speed and number of times the recording is replayed. So if we add a CAN replay and we drag over and a CAN trace, we can redock the windows so we can see both at one time. We right mouse click, we drag our recorded file into the CAN replay window object. As with other Windows utility, we can resize. We can change it from real time to a fixed rate, or in this case, an endless loop or a single play. We go online, we hit the play radio button, and we can see data start to stream up in the CAN trace window. If we right mouse click, because there is a DBC file, we can fix the scrolling mode and we can see the signals inside each of the messages. The CAN send object allows for user-defined messages to be broadcast onto the bus. In this instance, I'm going to be broadcasting a message and overriding the CAN bus. As you can see, when I stop the messages up in the right-hand corner, I see data, and when I hit the play button, the start button, it forces those values to a predetermined level. There are a few things to keep in mind when using CANLab with J1939, such as setting of the recording protocols and assigning the database files to the proper channels. By default, with the J1939 recorded log file, CANLab default sets the high-level protocol to raw data. To properly decode this, it needs to be set to a J1939 format. Also, because we can have multiple DBC files active in a workspace, it is important to assign each one to its specific device. CANLab CAN trace object has some unique filters that can be added to the CAN trace window to customize it for J1939 data, such as the PGN, source, and destination, as well as the priority of the messages. So starting from a raw workspace, we're going to add a J1939 monitor. We're going to add a recording. This is a pre-recorded file taken from an actual vehicle. We're going to add a database so we can decode those messages into signals. Under the database manager, we set where the database is going to be assigned. To this case, it's going to be assigned to the J1939 Monitor 1. Under the recording, we go to its properties and we set it to a J1939 message. We add a replay window. We drag our replay recorded file up to the replay window. We select endless loop. We then add a CAN trace window. We go online. We hit play. And we start to see raw data transmitting from the J1939 monitor. We hit the runtime customization, we can add the PGN, source, destination, and priority information from the database out of the recorder object. Going to a fixed format position allows us to go into each message and observe its individual signals. One of the features that makes CANLab a value proposition is that the core software includes a built-in scripting environment that uses a non-proprietary language, C#. Here we can see a few of the events and triggers that are available within CANLab scripting environment. This allows you to monitor bus traffic, set up triggers with a script, and cause messages to be sent or received or recorded, whether by a keystroke or by an event. We'd like to open up the seminar now to Q&A for Brian on J1939 or myself on CANLab.